Welcome back to section 4 of chapter 1. In this section, we're going to be looking at building functions from functions. This is also known as operations with functions. A lot of what we're going to look at today, well, first of all, you already know a lot of it because you dealt with it last year. But even then, a lot of it is going to kind of be common sense, but there's some stuff that's a little bit weird in here, so we'll see that when we get to it. Our learning targets for the day. We can add, subtract, multiply, and divide functions and find the domain of the result. We can evaluate composite functions. We can find explicit rules for composite functions. We can decompose composite functions because old functions don't die, they just decompose. Ha ha ha. And we can solve applications involving building functions from functions. I thought there was one on implicit functions as well. All right, so basic function operations. All right, before we get into the basic function operations, let's take a couple functions so that we have examples to work with. We're going to use f of x equals x squared plus 2x and g of x equals 3x minus 7. I made these two functions up. There's absolutely nothing special about them. It's just I wanted functions to use for our examples. So if we're adding functions, we just add them. F plus g of x is f of x plus g of x. In our instance, f plus g of x will equal f of x is x squared plus 2x plus g of x, which is 3x minus 7. Combine our like terms. We have x squared plus 5x minus 7. That's adding. We just combine like terms. Subtracting, basically the same, except we're subtracting. F minus g of x is x squared plus 2x minus 3x minus 7. When we subtract, remember, distribute that negative sign. Don't do something foolish. If you're going to make mistakes, make them worth it. That one's not worth it. So we'll have x squared, we have plus 2x minus 3x is minus x, and then negative 7 is plus 7. Pretty easy adding and subtracting. Multiplying, same basic idea. Fg of x is f of x times g of x. X squared plus 2x times 3x minus 7. And then when we multiply, we do have to distribute. Fg of x squared times 3x is 3x cubed. X squared times negative 7 is minus 7x squared. Then we have 2x times 3x is plus 6x squared. 2x times negative 7 is minus 14x. Combine like terms, which would be those guys. Fg of x, in our case, we have 3x cubed. Negative 7x squared plus 6x squared is negative x squared minus 14x. So that's multiplication. Division, same thing, we divide. Important piece here, g of x cannot equal 0 because that would be division by 0, which is generally speaking frowned upon, at least at this point in your life. Spoiler alert. But as long as g of x isn't 0, and so that's a domain restriction we talked about, all the other stuff, the domain's all real still. It doesn't matter. But here, g of x can't equal 0. We just plug it in. F over g of x is f of x, which is x squared plus 2x, over g of x, which is 3x minus 7. We could reduce if we can. We'd have to factor. This, we could factor an x out of the top, get x times x plus 2. That's not going to simplify with anything in the bottom. So we have that. And then the denominator cannot equal 0. So 3x minus 7 can't equal 0. We can add the 7 divided by 3. So x can't equal 7/3. There's the domain restriction. So those are the basic operations that, like, if I just gave you those problems and you had to take a guess, chances are you would do it right. Possibly with the exception of not getting the domain on the division one, just because you might not think about it. This next one, the composition of functions, is a little bit different. So we have our functions again. Now the composition, we have two ways of writing this, and they're both pronounced the same. This is f of g of x. It's f of g of x. And what it is it's going to take the g of x function and it's going to plug it in to the f of x function. We've done this before, actually. Any kind of vertical or horizontal translations, we replace the x with like x minus 2. That's a composition. So in our case, we have f of g of x. So these two things mean the same. My preferred way of writing it is that way. So anytime I write stuff, it's always that way. When I'm writing tests or some stuff like that, I will have to go back and change one or two to be the other way, just so that we have them, but I default to that way. So f of g of x, we're going to take the f function, which is something squared plus 2 times something, and we're going to plug in the g function, which is 3x minus 7. There we go. We could simplify it if we wanted to, but we're just going to leave it right like that. Yeah, we'll leave it like that. I also want to do g of f of x. So we're going to take the g function, which is 3 times x minus 7. Then we plug in f, which is x squared plus 2x. So the reason why I was thinking about multiplying it out was to see, are these two things the same? But if you're just looking at them, you can probably figure out pretty quickly that these two things are not going to be the same. If we wanted, say, f of g of 3, there are two ways we could do this. We could take 3 and plug it in up here, or we could do it piece by piece. We could find g of 3, which is 3 times 3 minus 7, which is 9 minus 7, so g of 3 equals 2, and then plug that 2 into f of x. We'd have f of 2, which is 2 squared plus 2 times 2, so 4 plus 4 is 8, so f of g of 3 would be 8, which is the same thing we would get plugging it into this equation. Only I think that doing it piece by piece is a lot of times going to be a little bit easier. Decomposing functions. This is just going backwards. We know that f of g of x equals x minus 1 squared plus 3 times x minus 1 minus 5. What do we see in here? Hey, we see x minus 1, x minus 1. Hey, that inside function, g of x, is x minus 1. So if I take that out and I replace it with x's, that tells us that f of x is going to be x squared plus 3x minus 5. So that's all decomposing is. It's just going backwards from the composition. Now, if it was all multiplied out, that would be much more difficult, but it won't be. Implicitly defined functions. So most of the functions that we deal with are explicit functions, where we can get f of x equals something with only x involved, or y equals something with only x. Implicitly defined functions, you cannot necessarily get y equals something. And these also go to relations, because not everything that we deal with is a function. They don't all pass the vertical line test. Something like a circle, x squared plus y squared equals 25. A circle can be a very useful thing mathematically. It's not a function though. We cannot get this to be y equals something. We could subtract the x squared and square root to get y equals plus or minus the square root of 25 minus x squared. And so we have two different pieces. We have the positive one and the negative one, which are both individually functions, but together they're not. And so just because it cannot be explicitly defined doesn't mean it's going to be a bad thing. So what we can do with these is we can plug in values. If x equals 1, what does y equal? If x equals 2, what does y equal? If x equals 3, what does y equal? And so we can find those that way. The other thing that we do with them is it'll ask, is this a value that satisfies a function? So let's say 3 comma 4. Is 3 comma 4 a value of the function? Just plug it in. 3 squared plus 4 squared equals 25. 3 squared is 9. 4 squared is 16 equals 25, which sure enough, it works. Yes, 3 comma 4 is a value for the function, or the relation. It's not a function, it's a relation. Then we could do another one. What about 1 comma 6? So we have 1 squared plus 6 squared equals 25. 1 squared is 1. 6 squared is 36. So 37 equals 25. That was a 5. No. 1 comma 6 is not a value that satisfies the function. It would not be on that circle. So that's how we deal with the implicitly defined functions. We cannot always solve for y. We just plug in values and we get a table of values. Then we can graph the table of values. So with that, I will see you in class. Until then, keep working problems, keep asking questions, and as always, happy mathing.